Hello everyone, I'm Satyajit Pattnaik and welcome back to my channel. You're watching the Dimensionality Reduction series and today's video is a continuation of the last video that's understanding the mathematics and statistics behind principal component analysis. In the previous video, we talked about PCA, how do we find various principal components given a statement, problem statement, how PCA comes into rescue, what exactly it does in terms of dimensional reduction. And we also saw a sample piece of code and I think we got a fair amount of idea about PCA, but yeah, let's try to understand more about PCA by providing a small example and seeing the mathematics behind it. If you're new to the channel, please subscribe and hit the bell icon to get notified on my future videos. So let's quickly get started. So likewise in the previous example where I showed you that, okay, let's say I have two different variables, let's say v1 and v2, and let's say the values are like 10, 8, something 3, 2, 1, and this is like 6, 5, 4, something like that. And we drew this like, let's say these are the various points which we got. And what we did is like we performed all the steps, right? We created a new centroid point, then we made this a new axis, and then we found the best fitted line, and then we performed a lot of steps, right, to find our final eigenvectors, right? So similar kind of concept, but I will be solving this particular problem using the mathematics. Okay, so let's say x and y here are defined as this. Now obviously y is nothing but, so y here is not the dependent variable. I'm just talking about I have two different independent variables. Let's consider v1 and v2, but just for simplicity from the mathematics point of view, I have just given it as x and y. Okay, so I have provided x and y. Obviously if I have to plot this, it's quite easy, right? It's going to be 10 and 6 somewhere here, 11 and 8 somewhere here, 8 and 5 somewhere here, 3 and 2 somewhere here, 2 and 2 somewhere here, and 2 and 1 somewhere here, right? Quite easy to plot, right? This is my x-axis and this is my y-axis, or you can call it as this is my v1 axis and this is my v2 axis, right? So my x and y are basically my v1 and v2. So in this video, we shall be understanding a little bit about covariance. I hope most of you might already be knowing about covariance, otherwise known as correlation. They are quietly, I would say the concepts of covariance and correlation are tightly coupled. Like covariance is nothing but how your variables are correlated to each other. Okay, like increase in variable A is also impacting or increasing. We can see the trend of increase in variable 2 as well, so, and vice versa. So based on that, our covariance is calculated. Now what is the significance of covariance in PCA? Let's try to understand that first. So the eigenvectors and eigenvalues of covariance, or you can call covariance as correlation. Okay, so the eigenvectors and eigenvalues of a covariance matrix represent the core of a PCA. The eigenvectors are also called as the principal components. They determine the direction of the new feature space, and the eigenvalues determine their magnitude. Okay, I hope that's clear. I'll just try to repeat it again. The eigenvectors or the principal components, the PC1 and the PC2 values. Let's say I'm just considering two variables, so definitely I'll get PC1 and PC2, right? So the eigenvectors, otherwise known as the principal components, they determine the direction of the new feature space, and the eigenvalues determine their magnitude. Okay, the goal of PCA is to find projection directions along with the variance of the projected data points is maximum, and the projector and the projection vectors must form an orthonormal basis. That means basically the covariance matrix naturally arises from the goal or objective of PCA itself. Okay, let's try to understand. Let's try to see the mathematics. Let's try to see the mathematics behind it. Now, as we already have the data, we would be more concerned about finding a. Let's talk about. I have to find a covariance matrix. Okay, I'll call it as C. or CM. Now covariance matrix is nothing but the covariance of XY, sorry, XX, covariance of XY, covariance of YX, and covariance of YY. Okay, this is my entire covariance matrix. Now what is the formula of covariance? Covariance, let's consider covariance of X and Y is equals to summation of I equals to 1 to n x minus x dash into y minus y dash divided by n plus n minus 1. Now what is my x? You can call it as xi and yi. X and y are my these variables xi and yi. Okay, and this is our covariance matrix formula, covariance value formula. Okay, so we are more concerned about x minus x dash and y minus y dash. So what is x dash and y dash? X dash and y dash are the mean values. So let's try to calculate the mean value of this one. The sum of this is okay, and the sum of this is okay. Let's say so the mean value will be this divided by 6, right? And the mean value of this will be this divided by 6. Okay, so x dash equals to 6 and y dash equals to 4, right? So here my x dash is 6 and y dash is 4. Okay, so I'll just write it down, x mean, and I'll make it as y mean. I'm just keeping it as 6 throughout and y mean is 4. Okay, let me just draw okay, so this is my x mean and y mean. So our next formula with respect to covariance of x and y, x and x, so the formula will be xi minus x dash, y will be replaced by x only, so xi minus x dash divided by n minus 1. That's basically x minus x dash square by n minus 1, summation of this. Okay, so let's create x minus x mean, and another there will be y minus y mean, and one more will be x. So let's consider this as a, this as b. This will be a into b. Okay, and let's do a square. That means x minus x mean square and y minus y mean square. So what is x minus x mean? I'll just quickly do this equals to this minus this. Okay, and I'll just make it. What is y minus y mean? Y minus y mean. Okay, I'll make it throughout. So 4, 5, 2, minus 3, minus 4, minus 4. And this is my, now if you look at these particular values, y mean and sorry, x minus x mean and y minus y mean. Now if you find a mean of this particular column, the mean will be 0, right? 4 plus 5, 9, 9 plus 2, 11, minus 11, 0. B mean 2 plus 4, 6, 6 plus 1, 7, 7 minus 7, 0, right? So this mean will be 0. So x minus x mean into y minus y mean. Let's try to calculate this. AB equals to this multiplied by this. Okay, I'll just, this equals to this into this. Y minus y mean square equals to 2 into 2, and I'll just expand it. Okay, so this is how my data looks like. So x minus x mean into y minus y mean equals to this particular column. Let me just draw it using a table. So what will be my this value covariance matrix? CM equals to So what is x of x? That means x minus x dash square divided by n minus 1. Okay, that means this equals to, sorry, sum of this divided by 5, right? This equals to sum of equals to sum of divided by 5. Okay, so my x minus x mean square and my y minus y mean square is this much. So square divided by 5. So this value will be 17.2. This value will be 7.6. Now what will be the other values? Which is nothing but x minus x dash into y minus y dash divided by n minus 1. So this equals to sum of this particular column divided by n minus 1. It's going to be 11.2. So let's write it down, 11.2. 11.2. Okay. I hope it's clear. So this is how my covariance matrix looks like. Now our main focus is to calculate the eigenvalues and eigenvectors for this covariance matrix. Okay, here as we already know that the total number of dimensions, or we just have two variables, right? Variable 1 and variable 2. So we will be getting two eigenvectors, right? So I hope it's clear with this particular slide. If not, you just pause the video and just write it down in the notebooks. I will just write down the covariance matrix, which is nothing but 17.2, 11.2, 11.2 and 7.6. Okay, now I have the covariance matrix. Now there is a formula called as C minus lambda I equals to 0. This is one of the formulas where I is nothing but my identity matrix. Okay, now identity matrix, many of us know that if it's a two-dimensional identity matrix, it looks like this, right? 1 0 0 1. If it is 3 dimensions, 1 0 0 0 1 0 0 0 1, right? Something like this. So let me just close it down. We are not concerned about the identity matrix. We know what is an identity matrix. My lambda is nothing but we are going to calculate the lambda, right? So let's see what the lambda is. We will, after we get the values of lambda, I'll tell you what exactly lambda means. Okay. So C minus lambda equals to 0. Let me write it down here. That means 17.2, 11.2, 11.2, 7.6. This minus lambda of 1001 equals to 0. This means 17.2, 11.2. I'll just go step by step very slowly so that you all follow the actual, you have an idea what exactly we are doing. So lambda into this, that means lambda into 1 equal to lambda, lambda into 0 equal to 0, lambda into 0 equal to 0, lambda into 1 equal to lambda, right? So you know matrix multiplication, right? Because this is a constant value. Your lambda is a constant value. This is a constant. And the constant is getting added to a matrix. That means it will be, it is multiplied to a matrix. That means it will be multiplied to each and every element. Okay. Similarly, now it's matrix 1 and matrix 2. So we are doing matrix 1 minus matrix 2. So it will be very straightforward. 17.2 minus lambda, 11.2, 11.2, 7.6 minus lambda. Okay, this becomes my new matrix. This equals to 0. Now there will be a concept of matrix multiplication. Like if this is my final output, let me just draw it in. If this is my final output, how do we get the equations out of it? Just go back to your basics. We have already studied this in our 10th and 12th. I think we just need a refresher, right? You just have to memorize it. So it will be a diagonal multiplication, and your output will be 17.2 minus lambda into 7.6 minus lambda minus 11.2 into 11.2 equals to 0. Now let me further solve this problem. This is nothing but, if I just do 17.2 into 7 into 7.6, let me write it down and then we will do it. So 17.2 into 7.6 minus 17.2 lambda minus 7.6 lambda plus lambda square minus 11.2 square equals to 0. Okay. Okay. Now let's calculate this thing. 17.2 into 7.6. 130.72. 130.72 minus 17.2 plus 7.6. 24.8 lambda minus, sorry, plus lambda square minus 11.2 into 11.2. 125.44. 125.44 equals to 0. So let's just convert it into a quadratic equation. This minus 24.8 lambda plus minus 130.72. 5.28. 5.28 equals to 0. So this is my lambda. So this is my quadratic equation. Now if we have to solve this equation, I'm not going to teach you how to solve a quadratic equation. For the time being, let's try to use the quadratic equation solver. Okay, there are a lot of solver in the Google itself. So I just have to pass. So my A value is nothing but 1. My B value is minus 24.8. Minus 24.8. My C value is 5.28. I might be wrong in some of the, like mathematically the values might, I cannot guarantee that whatever I'm doing right now, like the multiplication and all, it might have some deviations, it might have some problems. So I'm just doing as per like I cannot guarantee if this value is correct or not, right? Like it could be 131.72, it could be a human error for me, right? But you just try to understand the steps. How do we find the values of lambda? That's more important, right? So here we get the two values, 24.58. So I'll just write it down. So lambda 1 equals to 24.58 and lambda 2 equals to 0.21. 0.21. So these are my two lambda values. Now let's see, let's go ahead and let's further dig into this particular problem. From here, what I will do is, after this we have already got the lambda values. Our very next step will be from this particular point. So 17.2 minus lambda. Let's see, I'm just considering lambda 1. Okay, 24.58. So the matrix will be 17.2 minus 24.58, 11.2, 11.2, 7.6 minus 24.58. Okay, clear? Let me just maximize it. Okay. Okay. So this. So here we have a concept of eigenvectors. So let's say I have x1 and x1 and y1. These are my eigenvectors. Okay. So I'm just introducing my eigenvectors here. So this multiplied with x1 and y1 equals to 0. Okay, this is the formula. You have to understand this. Now let's try to solve this particular problem. 17.2 minus 24.58. 17.2 minus 24.58. That's minus 7.38. Minus 7.38. This is 11.2. This is 11.2. and this is 7.6 minus 24.58, 16.98 minus 16.98 into x1, x2, sorry, x1, y1 equals to 0. So if I just solve this particular problem, it will be minus 7.38 x1 plus 11.2 y1 equals to 0. This will be equation 1. The second equation will be 11.2 x1 minus 16.98 y1 equals to 0. This is equation 2. Now, there is one more equation which is nothing but the sum of square of the eigenvectors. So here I have defined my eigenvectors, right? X1 and Y1. So this you just have to memorize this also. The sum of the squares of the eigenvectors is also 0. You can consider this as equation 3. Okay. Now we have 3 equations. Obviously, we can solve this particular problem using equation 1 and equation 2, but let's try to make use of equation 3 and solve it. So let's say from here, what I can do is 11.2 y1 equals to 7.38 x1 holds true. That means y1 equals to 7.38 x1 divided by 11.2, right? So this value I will replace it in my equation 3. That means x1 square plus, instead of y, I am writing 7.38 divided by 11.2 x1 square equals to 0. That means I'll just solve it. 7.38 divided by 11.2. This 0.6. Let's consider 0.66. So 0.66 into 0.66. So x1 square plus 0.43 x1 square equals to 0. That means sorry, this is equals to, my bad, it's a mistake somewhere. Okay, my bad. So this is nothing, this is not 0. So this is 1. I'll just rub it. My mistake. Okay, this is 1. My bad. Okay, so x1 square plus y1 square equals to 1. Okay, so I will just rub these things as well. Equals to 0, the right side part, the RHS part. Okay, so this is equal to 1, this equals to 1, and then so 1.43 x1 square equals to 1. So what is x1 square? Equals to 1 by 1.43. So x1 equals to this root over, right? So 1 divided by 1.43, whatever, it's root over 0.83. So x1 is 0.83. So what is y1? Y1 is going to be this thing, right? 7.38 into 0.83 divided by 11.2. So 0.83 into 7.38 divided by 11.2, 0.55. Okay, so now I just minimize it and then expand it further. I hope you got the point. So I have my x value as 0.83 and y1 value as 0.55. Similarly, you have to follow the exact steps what I did right now for lambda 2 equals to 0.21. 0.21. Okay, here also you have to do the same thing. 17.2 minus 0.21, 11.2, 11.2, 7.6 minus 0.21 multiplied with x2 and y2. Okay, this equals to 0, and follow the exact steps. So here you will be able to find your x2 and y2. So ultimately, let's assume it as 0.5 and 0.5. Okay, so I hope it's clear. Now we are able to find all the x1, x2, y1, y2 values, right? So now if I just summarize everything, this is how my final output looks like: 0.83, 0.55, let's say 0.5 and 0.5. So this is nothing but my x1 and y1, which is also called as lambda 1, and x2 and y2, also called as lambda 2. So this is my final output, and you can call this as a eigenvector. Okay, so I think mathematically we were able to identify eigenvector values, and I hope it's clear. This is how internally this is how PCA works. Now, mathematically, you might not care about it, but yeah, theoretically, I think you had a good amount of understanding in the previous video. That's it for today's video. I will just try to wind it up. So I think we had a good understanding on PCA so far. The next video will be on linear discriminant analysis, which is also very much similar to PCA, but it has some, obviously it is little bit different from PCA, and we'll talk about the differences first, and then we will talk about how LDA works internally and how LDA is better than PCA in some cases. But yeah, in some cases PCA still does very good job, right? I'll also be sharing this particular file with you all if you want it, but I think you can pause and play from the video, and that I think that should be more than enough. Okay, in case if you have any doubts, you have my contact number and my LinkedIn profile, everything in the description below. You can just reach me out, and maybe I'll try to help you out in any of your problems. So that's it for today's video. Thanks for supporting my channel. If you like the video, please like, share, and subscribe among your friends. And that's it. Keep supporting and keep following my future videos as well. Thank you.